Thank you, Amos, for trying yet again to see if I can give a coherent talk. I think this is a sampling until success process, so the incentive is not quite right for you yet. I'd like to know whether we're aiming for success or failure. So what I'd like to do is discuss a topic which picks up almost exactly where Ariel left off, with value of information directed towards informing decisions, so the instrumental value of information in improving decisions. And I'd like first to review, I think, unpacking a bit the result that Ariel pointed to about what is the common sense idea that it can't hurt to learn before you decide. I'll unpack that result. That's a basic theorem of expected utility, because I think when we unpack it, we see, as always with substantive results, there are some delicate assumptions, and I want to tweak one of the assumptions with you, having to do with the representation of uncertainty by a single probability rather than a set. And what we'll see is that the shift over to the attempt to use sets of probabilities to represent uncertainty, one way of trying to accommodate some of what Michael was doing when he had a dimension representing uncertainty, which was supposed to be different than just degree of truth and degree of falsity. That if we use sets to try and capture that aspect and go through the same argument, we discover, to our surprise, there are some things we rather not know, that we would pay not to know. And I'll take you through such an example with statistical models for them. The particular case I'm going to is what's called Epsilon contaminated models. They're very common in robust statistics. And I'll show you how acquiring things you rather not know is a consequence of that approach. So this is the basic result in English. Then we'll look at the assumptions. If you can postpone a terminal decision in order to observe cost-free an experiment whose outcome might change your decision, then that information has positive value to you in advance. Notice the requirement here is that the information must make a difference in the sense of possibly getting you to act differently. Your opinions may change, but if the changing opinion fails to change your behavior, then the information won't carry positive value. It will just be of zero value. So the theory says cost-free information, non-negative value, and strictly positive as long as the information gets you to change your behavior. Let's go through it. The argument is old. It's been formulated quite clearly by I.J. Good. I'll use a version close to his, but you can find Frank Ramsey and some unpublished notes that had already formulated it. It's been around for a long time. So this is the schematic version I'll like to use. We'll try a little visual representation this way. I don't know which ones work, so I try them all. Here's a schematization of the sequential problem. You're there, box representing a choice node, oval, a chance node, and you're sitting where you have a decision between k terminal decisions. I'll unpack those in the next slide, basically choosing amongst k options now. Or you can postpone that decision, observe the random outcome of the random variable x, suppose it has m values, and then face exactly the same decision, except that now your information is modified by having learned the value of x. I have to make clear what it means to say these are the same decision. The learning of the x can't change the state, for example. I've highlighted a case where if we assume d star is best by expected utility standards of what you would choose now, and then you imagine hypothetically, well, how would I choose if I learned x equals x1? Maybe d star again is still best. X equals x2. Now I switch to d1. If even one of these branches has a switch away from d star, then from that initial standpoint, the expected utility of going this way is greater than the expected utility of d star. We'll go through. The theorem that proves that is the theorem that we're going to see is delicate. And that is the mathematical condition is delicate, so that moving from precise to sets of probabilities is enough to cause problems. Okay, so what do I mean by unpacking those terminal decisions? So let's just take a look and keep track of all the assumptions we've got here. So I'm assuming those terminal decisions are decisions under uncertainty for you. And so the rows are those terminal options, D1 through dk. There are maybe n states of uncertainty that you would use to formulate a simple decision matrix. And the entries in the matrix, the outcomes tell you the consequences as far as they're relevant to you of choosing a particular option when a certain state of affairs occurs. This is what I mean by the terminal decision. If there was no experiment, this is the way you look at it. And we're going to allow the notion of outcome to be about as general as you would like. Now, for purposes of proving the theorem, we have to know what kind of expected utility or subjective expected utility we're entertaining. And in this case, we're going to assume the familiar objective vanilla-flavored expected utility, that there's a ranking over terminal options, hypothetical options included, such that the agent's ranking is given by a subjective expected utility with a single probability on the states. Remember, the states are the states of uncertainty, the columns. Single probability on the states and a utility over the outcomes, the entries of the box, such that the agent ranks the options by subjective expected utility. And you're going to rank options by their subjective expected utility. This is, I think, a little bit more unpacking than we saw in RALs because I want to keep track of the states that are, I want to keep track of the states of the thermal decision from the states that you learned in the variable. Now, in this expected utility representation, there's an assumption that was made, whoops, this is not showing up on that, that the probability was act state independent. That is, if you go back to the representation I was using here, the probability on the states is independent of the act chosen. This is important for the result. RAL's version, I don't know, made this point exactly so clear. But you need to have this holding so that there needs to be act state independence with the terminal decisions. Otherwise, for example, dominance would not obtain in general for expected utility. But more importantly, and this is what I'll come to, let me skip the rest of this, that's not so important. What we'll come to in a moment is that if you allowed there to be act state dependence, then the result would fail. And in fact, I've already said that in this environment when we first had our first meeting, and I'll come back to that in a moment. But anyway, to remind you, I just unpacked these terminal decisions for you as those matrices. We haven't considered the particular random variable x, but it's going to be one that you are imagining you can learn the exact value of. And in going from your opinion there to opinion here, we're going to assume you're using the conditional probability as the update rule. So that what you're going to do is take your original opinions and update the distributions on the states, the columns, by saying now it's my conditional probability relative to the added information that x equals x1, x equals x2, and so on. And I maximize conditional expected utility in those cases. Now, the proof of the result is absolutely trivial once we've got all these assumptions in, and we have this law of total probability, or Tower theorem, however you know it, in place, which is that for arbitrary bounded random variables, the expectation of a random variable is the expectation of its conditional expectation, assuming, of course, that the conditional random variable generates well-defined conditional expectations. This is a basic result, just the law of total probability written out. And now you can see the proof of the value of cost-free information is immediate. We start with the value to you of deciding now, that's the expected utility, say, of maximizing expected utility from the terminal set of k options, call that t star. Well, by the law of conditional expectations, that is the expectation of ignoring the evidence, just choosing whatever the evidence is, just choosing d star again. The expectation of d star is the expectation of its conditional expectation. So if I thought of choosing d star after I saw x regardless x, the expectation of that strategy would of course be the expectation of d star, because I'm just choosing d star. But when I use the evidence, I allow myself to choose a different option, perhaps a different d, which means its value is going to be bigger than the value of d star for that value of x. And so I'll be averaging values that are bigger than the average value of d star, and there's your answer. So the utility of this sequential has to be not less than the utility of the best now. And as long as one of these red D's is not D star, I'm doing better than the conditional of D star in that state, so the average is higher. And so my current value for the sequential is higher than the current value for the terminal decision. And so we have what every good academician knows: never decide today what you can postpone to tomorrow. And again, what's critical is that the only way that the current best choice is the value, has the same value as the experimental play, is if and only if the new evidence doesn't change your behavior. So the evidence can be relevant and change your opinion about the states, but if that opinion change doesn't get reflected in change in behavior, the difference doesn't make a difference to you. And of course, the difference between these is then the value ex ante you would place on the experiment. You'd be willing to pay up to that difference to gain the information. And this is the backbone for doing Bayesian experimental design. Okay, back to the point about at-state dependence. You probably have pleasantly forgotten the fact, but this much of the story I had rehearsed here the very first time we had a meeting when Arnold was present. Because I took us on a different route then, and I said, one of the ways that Tower law breaks is if you have moral hazard, at-state dependence. And I went through a case with you that's known to game theorists, where you have two people playing a Bayesian game, and they have an opportunity for one of them to learn some information, and the other, of course, knows the information structure that the first one learned it. So the first one learns some information, the second one knows that the first one learned it, and they have a choice. Which game do they want to play, the initial game, or the game in which player one learns some information and player two knows that? Well, the Nash for the first game, Pareto dominates the Nash for the second game. That means they both rather not learn. How can that be? Because the game is such that there's at-state dependence. When I learn something, it changes my opinion about what you're going to do. What you're going to do is part of the states of uncertainty. And so when you have at-state dependence, you can have negative value of information in the form that is well known to game theorists. Open a basic game theory text and you'll be told, oh, unlike decision theory, in games information can carry negative value. You can't just ignore it. Why? Because, well, anyway, that was 4 years ago or whatever. I'm back again. More things you don't want to know. Instead of worrying about at-state dependence, let's modify the theory by looking at a relaxation of the Bayesian model where we use sets of probabilities rather than single probabilities to reflect uncertainty. There's a pretty large literature on this. There's a community, the SIPTA community, that meets every other year. About 100 people working on this principal part of their research activities. The idea for doing it, you can find in philosophy. Isaac Levi, one of my teachers was doing that in the early 70s. Peter Wally has this classic book that you can find about 1,000 pages. From a decision theoretic point of view, once you've got sets of probabilities, you want to know how to make decisions with them. One of the best known rules for working with sets of probabilities is the gamma maximin rule. You'll find it in statistics in the work of Jim Berger from the mid-'80s, and economists will know it from the very popular work of Gillow and Schmeidlove on representation for this decision rule from the late 80s. This is Journal of Mathematical Economics. The rule is very simple. When you have a set of probabilities, what do you do now? Well, for each probability, you can calculate expected utilities. And for each option, you worry about its lowest expected utility. It's a kind of security analysis. And so for the gamma maximin rule will say maximize minimum expected utility with regard to the set. Choose the least favorable distribution for each option, and then figure out which option's minimum is maximum. Just a minimax with regard to expected utility. A maximum, excuse me. And now we'll show you how with cost of how with this decision rule and sets of probabilities, cost-free information may be negative. And I'll do it using a phenomena that Larry Wasson and I investigated some years ago we call dilation. And this is the aspect of the new dimension of uncertainty, which you cannot get with a single dimension of probability. So this is what sits behind the decision theoretic negative value of information.
So let me describe the phenomena, and then I'll give you an example. Let's suppose P is a convex set of probabilities. So we're using this added dimension we have of representing uncertainty with a set of probabilities. And for an event in our algebra E, let P lower star E be the lower probability, the infimum, and P upper star E the supremum of the probabilities in the set. The set's closed, these are mins and max, but we're not worried about boundaries. This is not going to be a boundary problem. Let X be a partition from our experiment, taken to be finite, and then what we'll be doing is using Bayes' rule to update the elements of the set script P. So these are the conditional probabilities for E, which follow upon learning the value x little I. And then by definition, we'll say that the experiment X dilates the set of probabilities for E if, regardless of which observation you see, the lower conditional for E drops down and the upper conditional for E goes up. So the set of probabilities for E goes from a set to a superset, going up on top and down on bottom. In that sense, the evidence has increased the uncertainty about E in the very sense of uncertainty that the sets of probabilities are trying to model. This is what you can't do with a single probability, or single probability. The number will move, but the range doesn't, and that's what we're talking about. So in this case, this is just the definition. So if you've got a case where, if this notion is not empty, then you've got evidence that is causing an increase in uncertainty, in the sense of uncertainty that the sets are meant to make salient, the new sense of uncertainty. Okay? So this is the opposite phenomena of what you're used to hearing about regarding shared evidence in Bayesians coming to agree. You can imagine these probabilities coming, the set being reflective of different experts, two at least. And to say that the set's dilating is to say the experts had less uncertainty in their opinions in terms of difference before than after, and they've just gone further apart. And I'll give you an example of dilation in a moment. It says the evidence is sure to increase their uncertainty. It's the opposite of the merging of Bayes postulation. Okay, here's a little toy example which captures relevant features, key features of dilation. Suppose A is an uncertain event. So it's one of these events that we're allowing ourselves to have a range of probabilities. Suppose I'll make it nearly maximal, and just to make it dramatic. So the upper probability of A is about 1, and lower probability of A is about 0. Let's introduce a fair coin. We have no problems recognizing this as a fair coin, so the probability of heads tails is precisely half. And we believe that the coin is independent of the event A about which we're uncertain. So I'm using A as a randomizer or a mixture, however you want. So now I've got a 2 by 2 table. Okay, and let me define the event E to be this diagonal. Why? Because regardless of the probability of A, the probability of E is a half. It's a half A plus a half not A. For every probability P of A, that gives me a half. And so E is an event whose probability is determinate, like that of heads and tails, a half, regardless of the distribution of A. Randomization does for you, by the way, when you do random sampling. It gives you a quantity like E whose expectation has a precise distribution, even though you're uncertain of the anyway. Another statistical case, E is pivotal. It has a distribution that doesn't depend on the uncertainty of A. But now you see the toy example of dilation. Your probability now for E is a half, precisely. But if I let you learn H or T, then the probability of E given H is just the probability of A, which is unchanged, 0. And the probability of E given tails is 0. So we've gone from a precise probability of half to conditional probability of E that's virtually maximum. And now if you're doing lower expected utility as a gambling assessment, you see what's happening. I mean, you can see right away how we're going to have negative value of information. Right now, a fair money bet for you on E is worth 0. But so $1 if E lose $1 if not E. It's worth 0 to you now. But if I let you see the value of the randomizer, its lower expected value drops off to -1. you can see how the negative value of information is going to be just sitting around the corner here. And that's, I think this is just what I said to you in English. I can skip the slide. Here's the numbers that would do it. Terminal option D1, lose $1 if E, win $1 if E complements, a fair gamble, it's indifferent to 0 for you. If I gave you a choice between that and a fine of 50 cents, you'd say, take the gamble. I say, okay, how would you like to postpone the decision to learn how the coin came out? Of course, once the coin comes out, the gamble, terminal D1, is now got a lower expected value of -1, regardless whether heads or tails. And under those conditions, you would choose a fine, which is only 50 cents. So the value of the information is -50 cents. You'd pay up to a quarter not to learn it. I've tried this with the dean of my college as a way of setting up overload. I said, as a philosopher, I know how to set up courses where every lecture is a dilation lecture. And so the students will be advised not to come, and of course they'll be very happy. And I don't have to go and show up, right? Because there's no one in the class. And they'll have to pay tuition for this, which will be fine, because they should pay not to show up. And I said, I'll take a big overload. But I'll take a big overload. My dean is expert in stochastic processes and computational finance. He really threw me out. Maybe you could try it at this college. Right? Might work. Okay, so a few words. Where am I? I'm on time. I'm sorry.
No, you're good.
Just a few minutes more. So, because I want to get to the Epsilon contaminated model. So, the heuristic example involved a coin that was independent. And it turns out if you give me coins, and I have any set of probabilities, I can create those kinds of strange events, like the randomized events that will dilate. So independence is sufficient for dilation. If you just give me independent events, I can bring them in and make those kinds of events easy. That's not a problem. And also, and this is perhaps a little bit more important, independence is necessary for dilation. In the case I gave you, the set of probabilities includes, because they're all defined that way, independence between the event I'm learning and the event I'm unsure of, A and E. A and heads were independent. Now, it doesn't have, in the example I gave you, every distribution in the set made A and heads independent, because I said the coin was independent. It doesn't have to be that way. I'll give you examples or not. But nonetheless, there must be in the set, if it's a convex set, some distribution that makes what you're learning and what you are unsure of independent, if there's dilation. That must be. And the reason I introduced this is a rather familiar measure of association in this kind of 2x2. I'm looking at the probability of AB divided by the product of the marginals. If they're independent, that's independent. If they're independent, that's 1. That ratio is 1. If it's greater than 1, it means they're positively associated. If it's less than 1, it's negatively associated. And it's an easy proof that if you have dilation, then it's not just in 2x2 tables. If you have dilation, then there must be a distribution in the set that makes the conditioning events independent. The events independent. Now for the Epsilon contaminated model, to show you that this is not just quick stuff. One of the most popular uses of the sets of probabilities, both in robust statistics and in Bayesian approaches, is to think of the set as generated in the following way. I have a model I'm reasonably confident of, model in the sense that we've been discussing here for generating the data. That's P. But I'm unsure really what the real process is for generating the data, and I'll say the data come from, with probability 1 minus epsilon, my intended model P, but with epsilon, I don't know what, outlier of some sort. That generates a set of distributions whose focal point is this distribution P. Now, for thinking about it in our terms, it's nice to know that this model is equivalent to giving you lower probabilities for the atoms. It's a little bit of work to prove it, but this set is equivalent to saying, give me the atoms of the algebra, put a lower probability bound, that is, I know what the probability of each atom is, and then give me the bound. The result of that is this. I'll show you a picture in a moment. There's a lemma, which is that if you have epsilon contamination model with dilation, the whole thing reduces to a sub-case of 2 by 2 with dilation. So looking at the 2 by 2 case is no loss of generality. Here's the equations. I'll show you the picture in a moment of what's going on with epsilon contamination and dilation. You'll get dilation. So S of P tells me, remember, capital P here is the focal point of the epsilon contaminated model. The 1 minus epsilon P and then epsilon anything else. So call that the focal point. So I'm asking, under the focal point, how much association is there between the row and the column? If it's positive, then epsilon, the size of the set, has to be at least as big as that. If it's negative, it has to be at least as big as that. If the focal point of the surface, if the focal point of the epsilon contaminated sits on the surface of independence, then you're stuck. You're going to dilate. Let me show you the picture of this. So what I've got here is a 2 by 2 table with 4 atoms, and I've organized the atoms into rows and columns. And what you're seeing is a surface of independence between the rows and columns. That is, this is a tetrahedron. Inside this is, each point in here is a probability on the 4 atoms. You've seen this sort of simplex before. This would be the point. This would be the point 1, comma 0, 0, 0, 0, 1, comma 0, 0, and so on. And so every probability distribution is an average of those 4 points, puts us inside the tetrahedron. That's the surface of independence that makes the rows and columns independent. What does an epsilon contaminated model look like in this case? Remember I said it gives you lower bounds on the atoms? Well, the lower bound on A1 will be given by a plane that's parallel to the face, that would be over here. The lower bound on A2 would be a plane coming in this way, A3 this way, A4 up from the bottom. Basically, I've got 4 planes that are parallel to the original faces. It creates another little tetrahedron. And so the epsilon contaminated model itself sits as a tetrahedron in here with faces parallel to the big faces. Just move it around, string it short. Any one of those is an epsilon contaminated model. If the barycenter sits on the surface, you've got dilation. If it's off, then it has to straddle the surface, and that's what those inequalities do. So that's the picture for what's going on. Okay, you might say, so much the worse for Bayesian sets of probabilities. I'm a Dempster-Shafer guy. Okay, Dempster-Shafer guy. In the epsilon contaminated model, every epsilon contaminated model is a complete function, and Dempster updating is Bayes updating in the epsilon contaminated model. So every equation I just gave you goes through without change for the Dempster-Shafer theory for the epsilon contaminated model. They don't give you much of a decision theory. I've always prodded hard for a decision theory. It's never told me quite how to use them. But I know that the belief functions are expanding exactly. It's the Bayes theory in this case. What I've given you is also Dempster-Shafer theory for the epsilon. Okay. So, down toward the end, dilation creates a new challenge for design of experiments, of course, because now it's not good enough that the evidence is cost-free. It's also got to be of non-negative value, which is not ordered. I would say the significance is heightened by the following result. Let's consider imprecise models, sets of probabilities, which obey the following neighborhood requirement. Suppose I start with a symmetric, uniform probability on a set, and there's a neighborhood in the set. So the uniform's in there and some other distributions in there. Then to say it's symmetric is to say permuting the atoms, or permuting the elements, the permuted distribution is in there. So in that sense, the neighborhood is symmetric around the uniform. So any distribution, any class of models, or any model that satisfies the symmetry is going to experience dilation with the exception of one model in all, that's the density ratio model. Those of you who study robust statistics, density ratio model is a model given by giving the ratios of probabilities and holding those inequalities, because that's what the conditional probabilities are given by, and that protects you from dilation. But every other model I know of in robust statistics, that's a neighborhood model, every other one of them will be susceptible to dilation, and hence the negative value of information if we're using anything like lower expectations. So summary, the basic expected utility result that cost-free information has non-negative value does not extend to imprecise probability decision theory when you use anything that looks like lower expectations as the decision rule. It covers a lot of cases. A lot of decision rules, though they may not start with lower expectations, will eventually say, okay, use lower expectations to either tie break or build in some security to choose them. And of course, dilation of sets of probabilities is a general recipe for creating cost-free data that do have negative value. And so given the prevalence of dilation in the sets of probability world, I would say there's an aspect of the value of information that uncertainty brings, which is not the Bayesian story, when all you do is switch from single probabilities to sets. I would say anything that's beginning to look like what Michael was asking, one of those dimensions is bringing in exactly this. I think we better be prepared to think about information having negative instrumental value, even though it's cost-free. And I'm not charging you for the calculations, though I have charged you about a half hour of your time for this.
I'm sure there are comments on this.
Thank you. Excellent as always. But I have an issue.
You want to invite him next time?
No, he should come. He should come. So I have an issue with the interpretation of negative value that you have here.
So you won't let me take the overload of courses?
No, you can. Yeah. So the issue is because you compare two basically, you compare oranges and apples in a sense because you change your information structure. So in each case, I maximize my utility. But in each case, it's conditional and based on a different information set. So it's not, so the interpretation of negative value, I'm not sure that it's really, I understand everything that you do.
So I'm not understanding what you're saying I'm doing wrong. I mean, I think you're slightly saying I'm being unfair to the Bayesian, if that's what I heard.
No, I think the comparison is done on different information structures. So then I don't think that you can call it negative information in this sense.
So this is what I'm
Because
not
you
understanding.
add-
So I'm not understanding, I'm sorry, I'm not understanding what you mean by different information structures. I mean, this is the common setup for both problems. The difference is that in the one case, we're allowing an agent or an entity, whatever, to represent uncertainty with sets of probabilities rather than a single probability. Other than that, it's the same structure. So what's different? Maybe I'm missing something in what you're saying.
Well, I don't think that I would call it, I see the mathematics here, but I don't think that you can call it negative value of information, even if it's cost-free. What you have here is you change somehow the informational structure, or you added a piece or something, but then your utility is defined actually on a different information set. So would you still not?
I'm sorry, I'm being very thick.
Well, I think I understand what Alex was trying to say. So isn't the top the square person?
Isn't the person in the square situation, if you thought of it in Bayesian terms, maximizing expected utility, integrating out over all of X possibilities?
Yes, and I was saying the same, in the case I was doing, the same thing would happen because, again, in this case, having learned X1, we just had two branches, heads, tails. The lower expected value over here was what was being used to decide. And we knew in the example I gave you, if you postpone the decision, you would adopt the fee of minus 50 cents.
Why don't you go to that slide, Teddy, because I think that makes it good.
So I didn't write it up as a chart, in the chart in exactly the same way.
There.
But this is what we're looking at. The sequential option, you're going to see the outcome of the coin flip, heads, tails, and then choose between the same two options, which is an even money bet on that diagonal event E, which you win $1 if E, lose $1 if not E, and pay a fine of 50 cents. But when you're using gamma maximum to make that choice at that lower box, minus 50 cents is better than the gamble conditioned on the outcome of the coin flip, because the gamble conditioned on the outcome of the coin flip has a range of value whose lower value is -1. So given a choice between an option whose lower value is -1 and a value of -50 cents, I choose -50 cents. So I know I'm choosing -50 cents, either heads or tails, and the ex ante expected value of that is -50 cents. There's no doubt that if after I flip the coin, I'm choosing -50 cents, either heads or tails, ex ante, the value to me of that branch is precisely -50 cents. And that has a value lower than the ex ante value of the terminal option D1, which has an expected value precisely of 0. So I choose the bet D1 now, and will even pay you up to 50 cents not to be presented with the evidence. That's where I don't see, I mean, I'm trying to be exactly parallel one to the other.
Okay, if I can.
Yeah, please.
The chairman said. I think the point Amos is getting at is in the initial decision, we're using expected utility, and then when we move to the sequential, we're using the maximum. So it's the maximum that's.
Okay, so so let me respond to that. I'm always using gamma maximum. It's just that in the
It
initial
coincides
case,
with
it
the
coincides. They're well defined. These are constant expectations over the set. So the expected value is the lower expected value.
But I think that may be the sense in which you say they're different.
Well, if you wanted, I can introduce a little bit of interval values here if you really want to see the gamma maximum picking up the minimum. I mean, if you want those not to be exact, remember dilation just requires that the lower and the upper expand. I was starting with a degenerate case where the lower and the upper were equal. If you want, we can separate them a little bit and then we'll get dilation. And then I'll be using gamma maximum, not expected utility, all the way through. This is just a special case of gamma maximum. So now I understand what the worry is. But no, gamma maximum reduces to expected utility when you have a single probability or single expectation. That's the reason it's been advocated by the IP community as a generalization of the Bayes theory, so that when the set collapses to a single probability, you get back expected utility. So that, I think that's maybe.
I just wonder whether this will be a similar. I just wonder whether this is a similar issue about terminology, because the X1, X2, what you have here, I wouldn't call it information, I would call it a message. Because it's it's
Okay.
not the.
I mean, that's the picture again, yeah. So you want to call these messages, that's fine. But they're messages that the agent accepts as communicating information, because the agent conditions on it.
But in my previous example, in the real case, the agents unfortunately they treat them. They're always changing their hypothesis. In this case, changing their distributions.
Yeah, they may well be changing their distributions and everything.
But if you're going back to my glaciologist cases, in that case, when they observe the X1 and they decide not to change the distribution, so there's an option you can change it or not change it.
So what we're assuming here is that this is set up as an experiment, so that the agent agrees that upon receiving the message x equals x1, the agent has agreed that's the truth.
Yeah.
I mean, this is an experiment that the agent, I mean, supposing there was no problem in understanding the experiment that way, that the message has a correct and accurate signal of how the random variable value is.
So that's partially is because
We could build in a little bit of noise measurement error in the x's if you want, but again, that's just adding a slight extra layer in here. I mean,
so
it's
it's
not
to
going
do
to change
with
the basic
to do with the task. If the task is to define whether x1, x2 is arrow or not arrow, alternatively the task is to try to optimize your distribution models, and that there's the two different tasks
So
involving in the same sum model and winner.
Let me remind you, this is the picture and exactly the same interpretation that was being used to explain this theorem. So if you don't like it the way I'm using it, then you're not going to like the defense of this basic result from expected utility. So that part of the story doesn't arise with the sense of probability. That part of the story is common to both. So if there's something about the scenario of the sequential decision that is missing something about information, it's being missed in the expected utility analysis as well. And that's the analysis that supports the initial result about cost-free information having non-negative value. So that's common.
I have a quick question, well,
Sure,
maybe it's
sure.
not so quick.
Okay.
It seems that the use of the max-min criteria in your example with the interval probabilities is playing the same role as dependence between the state and the decision is in the other counterexample. Is there a way to give this an interpretation in terms of somehow inducing dependence? I couldn't see it.
I didn't see it. I thought it's an independent line of, it's just another assumption. Remember, one assumption was that you had a single probability with act-state independence. And the game theory example I gave last time has a single probability, but with act-state dependence, negative value of information.
Right.
Now we're keeping act-state independence, but with sets of probabilities.
And I'm wondering if the max-min criteria is inducing
Okay, I'll
something
think
like
about it. I'll have to think
But
about it.
I didn't see
It doesn't strike me as that way. I thought at least I was giving a different line. If you're
Yeah.
telling me I'm giving you the same talk over again, I don't.
No, I wasn't doing that.
I have a question. When you collect information about this extra random variable x, is there any idea that the reason you're collecting more information is because this is going to give you a better assessment of the consequences of your action?
That's the point.
Or is it random?
No. We assumed this was experimental design. That's the whole point. X was being chosen. And the Bayesian story, in the case of cost-free information, is if it's cost-free, nothing will hurt. I mean, if you have a choice of different x's, x1, capital X2, you can only choose one. You choose the one that has the greatest expected value. But it can't hurt to go look. That's the story. It's just a question of how efficient you are in choosing the best experiment. Here, there's actually a tip-in the other way, which says if you're sloppy in the design of your experiment, even though it's cost-free, you may wind up in a situation where you're actually putting yourself in an inferior. That's what's being highlighted here.
Thank you.